We're going to finish up chapter 21 today. We're going to talk about the energy that we can get. We have chemical energy, which is what we use mostly, and nuclear energy, okay? Chemical energy is associated with making and breaking chemical bonds when we burn natural gas, when we use gasoline, when we use coal, when we burn coal, that kind of stuff. And you can see that we get a lot of our energy. Look down here, we get 30% from gas, 38% from coal, so that's 68%, and then we get oil in there. We get a little nuclear. 19% of our energy comes from nuclear, okay? If you look at France, they get 76% of the energy from nuclear, and the reason for that is they don't have fossil fuels anymore. They don't have any of those reserves. These are older countries, much older than us, so they've run out, okay? Here you can see China uses a lot of coal. It's really dirty, and they have some serious issues with it in there. The worldwide you can't see so much, but 39% comes from coal, 22% from gas, a little bit of hydroelectric. On the whole, we get about 11% in the whole world of our energy from nuclear, okay? So the US is a little above that. China, very little, and France, okay? So if you ever go to Europe, you guys, you'll see they use a lot of different ways of getting energy than we do. And the reason for that is they don't have these huge amounts of oil and coal, natural gas like we do, okay? So nuclear energy has an enormous amount of potential. There's so much energy in there, but it's also, people are very scared to use nuclear because if you have a nuclear reaction, if you've ever heard of Chernobyl, nasty things can happen if it's not taken care of. So it's a great way to get energy, but it also has some serious bad consequences if it goes wrong, okay? Nuclear energy is due to changes in the nucleus, plain and simple. That's why it's called nuclear, okay? Again, we said there's an enormous amount of energy there. So you change atoms from one atom to a different atom, and you absorb the energy that's released when that happens, okay? And again, 13%, here it says 11%. Funny. Anyway, we get about 13%, 11 to 13% of our energy from nuclear power. Okay, the way they do it is called nuclear fission. Fission means to break up, okay? Here you have, our source is uranium, okay? They add a neutron to uranium, and then you get these substances. And when that happens, basically, they take a particle and they, break it down into smaller pieces. And then we use the energy that is given off when that happens, okay? So uranium is a source. Uranium is a non-renewable source. So some people think nuclear is renewable. No, it's not. We'll run out of uranium someday. We have a lot of it, but I mean, it is not a renewable energy source, okay? So a heavy nuclei can split it in many ways. There's some things, what they do is they basically bombard the uranium and break it down into smaller pieces and then use the energy from that. Okay, they heat up water, makes turbines spin, you get electricity, okay? That's exactly what happens in a hydroelectric power plant is you turn a turbine and you get electricity, only they use running water to turn the turbine. If you have a coal burning plant, you burn coal, it heats up the water and it spins the turbine. So basically you got to figure out a way to spin the turbine. How you do that, if you use the heat given off from a nuclear power plant or nuclear power reaction, sorry, or from hydroelectric or whatever, but it's turn the turbine and get the electricity. How you do it determines what type of energy you're using, okay? Okay, nuclear fission, again, is a bombardment of a nuclide, and it starts a process, and you can see you got one neutron in it, breaks down, and then it keeps bombarding, and it breaks down, and it breaks down, and when they're released, when they're broken down into smaller pieces, they release energy, okay? And that's the energy they use to produce electricity. Okay, it's a chain reaction, obviously, and they do control it through graphite rods and some things like that. Here is a nuclear reactor. If you can see it, here's the turbine and electricity. This is the end part. This is all, any type of power plant that you have, this is the same. But how you get the steam depends. Now here's a nuclear reactor. It has uranium rods come in, and then there's other rods. They're usually graphite that come in and control. So if you push these up, it slows it down. If you move them down, it speeds it up. So these control the rate of reaction. But again, you get energy released in the form of heat. It makes steam. The steam makes the turbine run. Okay, so the steam could be produced by burning coal, by burning natural gas, whatever. So this part changes depending on your plant, but the steam and the moving the turbine, okay, also you can have a hydroelectric plant that runs across and turns the turbine. So this part is always the same, okay? Okay, here you can see in the nuclear reactor, again, you have fuel rods. These are usually made out of uranium. And then you have these control rods, and they're usually made out of like graphite, a carbon thing. And they can absorb neutrons. As you move it down, you slow down the reaction. As you put it up, you you make the reaction go faster. And water is this tank is filled with water. It helps moderate it and keep it cool so it doesn't get too hot. Okay, so control rods can block the paths of neutrons, and that's how it slows it down. And it has to be, you don't want it to get to a supercritical mass, because if it does, then it's going to go kaboom. It won't be able to control the energy that's released. Okay, one of the biggest problems with nuclear power is when you're done with the reactant, you have this spent fuel, and it's plutonium that they use to make bombs. So there's a lot of issues of what do you do with this spent fuel, because its half-life is huge. It takes thousands and thousands of years for it to break down. So they're trying to figure out a way to reprocess it. They also have to store it securely, because terrorists getting a hold of plutonium would not be a good thing. So there's a lot of issues with the nuclear waste. Okay, they're basically stored in pools at the reactor site. They have not come out with a place to store them. Some of the reasons where it has to be extremely stable. You don't want an earthquake or something, water to leak in there or something like that. Plus, who wants nuclear waste stored by them? Not a good idea. Okay, the original intent was that the waste would be transported to a reprocessing or storage site, but they haven't developed that yet. They don't know how to reprocess it, and they don't have a storage site. Okay, there's a lot of political opposition to where to store it safely. You don't want that waste being stolen. It's got to be protected. There's just so many issues. And the other thing about a nuclear power plant, it only lasts so long. And then it has to be encased in cement, and then it has to be guarded, because you still have that waste there, and you don't want it getting in the wrong hands. Okay. There's also what they call nuclear fusion, which is kind of a safer thing, where you take small atoms and you combine them. So fission is breaking down. Fusion is fusing them together so they get together. Those reactions, they're called thermonuclear reactions. Okay. If it's possible, it's easier to use this, but it's an easier method, and it would be a preferred source of energy because, again, you don't get the waste. Okay, it's safer. However, you have to have extremely high temperatures and pressures to get the nuclei to fuse. The problem is, what do you do that in? Because it's not like you can do it in a simple container, because it would melt the container. So here's an example of two different hydrogen isotopes, and then you can get them to fuse. And then again, it releases energy, and you can absorb that energy, and you can heat up water, and you can make power. Okay, this is achieved using the atomic bomb to initiate the fusion. And then it's weird because first it initiated fusion, but it's not really what you want that energy to be used for. Okay, we don't want nuclear bombs. They're awful. I mean, if you ever want to watch videos of what it did to Japan, it's just not a way to go. Okay. We do, again, we do have radiation in our environment. Sometimes people have it. If you have a basement, you might want to check for radon. Radon's naturally occurring in the soil, but in your basement, you might have some issues with that. And they do have little kits that you can send in. And if there's an issue, you need to have it dealt with, because it could cause cancer. Okay. There's ionizing radiation, which is more harmful to living systems, and non-ionizing radiation, such as radio frequencies. Okay, so we have all kinds of radiation. It's all around. It's something you need to protect yourself from. It's kind of crazy, because in the right amounts it's a good thing, and the wrong amounts it's very harmful. So most of our living tissue, most of us, is water, which is ionizing radiation. Okay, water, remember, when it ionizes you take two water and you end up with H3O, which is acid, OH, which is a base. That's a natural occurring thing. Okay, when it creates an unstable, you get too many of the OH. Okay, and that can end up causing cell damage. So you got to be careful. Again, this is something, that's why they use the measuring badges and the all those things to make sure people haven't been exposed to too much radiation, because you're going to get cell damage. Okay, what does it do? Here we talked about alpha, beta, and gamma. Okay, and alpha, your skin will stop it. Okay, so obviously alpha radiation isn't very harmful. Beta, you can see, can penetrate your skin. Penetrate your skin and get down to the next level into your other tissues. And you can see gamma can go right through you. So gamma is definitely not a good thing. Okay, the damage to cells depends on the type, how long, the length of exposure, whether the source is outside or inside your body. So you can have all kinds of things. But outside, obviously, gamma rays are by far the most dangerous. Okay. Inside the body, alpha radiation can cause most harm. That's kind of crazy if you think about it. So if it gets in, it's not good. Okay. So again, the damage, it depends on your exposure to it, how long, and so on. Okay. So we are constantly exposed to radiation. What are safe amounts? Okay. So here they have a chart, and you can look through that. Setting the standards for safety is very difficult, because it's not like you can expose people and say, oh, geez, you got cancer. Sorry, thanks for being in our study. You can't do that, okay? So what you have to do is you have to look out at what's already there for the standards. I mean, because like I said, you can't expose people to radiation and see what happens to them. What happens if they do develop long-term health issues? Are that you're responsible for that. So you can't do research like that. Okay. But again, they look at the growth regulation mechanisms of cells that result in cancer. You can see some of them. The abundant ones, we have potassium, rubidium, thorium, uranium, and they set standards. But again, it's really hard because you have to look at what's already out there. You can't expose people to radiation and see what happens to them, okay? So it's kind of a weird thing, okay? So short-term exposure is 600 REM, radioactive emission something, I can't remember, is very fatal. Okay, so again, the badges, you can see the effects. 0 to 25, really no detectable effects. 25 to 50, you're going to have a slight decrease in your white blood cell count. Okay, so it'll decrease your immune response basically. 100 to 200, you're going to feel sick, and again, you're going to have a mark. Your white blood cell is going to go way down, and your immune response is really going to be bad. In 500, you can see death to half the people that are exposed to that. So half the people that are exposed to 500 die. Not a good thing within 30 days. So again, and you can see where you can get exposure. Radon I talked about already. Rocks and soil have a little bit. There's cosmic rays that come in. We have radioisotopes in our body already. And then we can add medical x-rays, nuclear medicine, and there's some consumer products. So we have man-made sources. If you don't remember that from environmental, those are called anthropogenic, and we have natural sources. Okay, and again, it just depends on your exposure of, all the other stuff. The average exposure per year is 360, and we have millirems. So 600 rems is a different thing. Okay, and again, it just depends on where you're at, what you're exposed to, and so on and so forth. And I think that's it. So we are done with chapter 21.